So, good evening, and I welcome you again for the doubt session of the basics of FEA class. And this is the final week of our course. So let's end things today. And so this week we studied time-dependent problems. And earlier last week we left on the eigenvalue problems. And in time-dependent problems, as just like other classes, I'll quickly go through the content of the this week, and then we'll discuss some problems. And meanwhile, you are welcome to present your doubts. So the basic we started with a basic equation that covers all different types of time-dependent terms and all derivatives of x as well. So this is what this PD looks like, and so we have studied different types of differential equations. So some had second order derivative term and some had fourth order derivative term. So we've covered both of these here, and we have different time derivative terms as well. So specifically, the cases that we actually practically study are three types. First is the transit heat conduction equation, that is also known as the parabolic equation, that only has a second order derivative term with respect to x and a first order derivative term with time. Then we have vibrational problems of the axial bar, where we have a second order derivative term for x as well as time. And then we have vibration of beam problem. So beam, as you know, that it's a fourth order derivative with respect to x, and apart from that, we have a second order time derivative term as well. So solution approach for the time dependent problems is as follows. First, we perform a spatial approximation. We integrate in space to get rid of the space the derivative term with respect to space, and so that our partial differential equation gets converted into an ordinary differential equation with respect to time only. So we get rid of the spatial terms first, and then we deal with the temporal terms, the time derivative terms with temporal approximation. So we'll see how we do it later. And then just like that, with this second step, we get an algebraic a set of algebraic equations, which we solve through assembly of matrices and vectors, and finally we apply the boundary conditions, initial conditions, to solve for the final result of. So the thing that is different here now is that we have to perform a temporal approximation as well before reaching the final form of algebraic equations. So how we do this? So spatial approximation, I think it must be, you must be familiar with it now. We have been doing the past weeks. So in spatial approximation, we approximate the. So first of all, the way we approximate the solution now is in this form. So we assume we make an assumption that the time dependence and space dependence is separable, which is quite true in most of our problems that we solve. In some places that it so happens that it doesn't work very sound, but there also we get some approximate results. So we can make this approximation comfortably. So we assume the shape function to be a purely a function of space terms, and then the our nodal values of the solution variable, we assume that to be a function of time. So we have our we just like the usually we get our weighted residual statement, uh, and we get our required stiffness matrices, mass matrices, and now we are left with the variable terms, this u dot and u double dot. These are actually derivative terms. So this statement is not completely an algebraic equation. It is indeed a partial an ordinary differential equation. So now since we have converted our PD into an OD, we perform the temporal approximation. So here we'll see the cases one by one. So for our heat conduction equation, we want to remove the u double dot term, and also this m2 term. Sorry, the k2 term would also not be here. This term also be removed. So in case of heat conduction problems, we only have this first derivative of time with respect to time. So this kind of approximation is taken care by a family of approximation known as alpha family of approximation. So this is what the approximation for alpha family looks like, and uh, in this alpha family approximation, there are certain different cases. So we can change use the required value of alpha to choose between the type of method we approximation method we want to choose. So in this alpha family, we first have the forward difference method where alpha equals 0. Then we have backward difference method where alpha equals to 1. And then for alpha equals to half, we have this method is known as Crank-Nicolson method. So, as you would have studied that the backward difference and the Crank-Nicolson method are unconditionally stable. But there is the problem with the with forward difference method that it is conditionally stable. So, what is the condition for its stability? That this statement should hold true. So, our time step should be in a should be less than certain limit, which is not the critical time step. Then this method works fine. So here we performed this approximation and got our final algebraic problem. So I won't go into much details of this. You have done this. So we get our final statement. This here. So this is how we deal with the parabolic equations or time dependent problem with first derivative term. Then if we have second derivative term, then this kind of approximation is handled with an integration scheme known as Newmark family of approximation. So here we use these statements, and so we now have to approximate first derivative as well as the second derivative. So we can approximate the primary variable u and its first derivative with these statement, and to get the second derivative, we can substitute these value back to the main equation, and we get these terms. Okay, so we have this. Yeah. So just like alpha family of approximation, Newmark family of approximation, we have certain different approximation methods depending on the type of the values of alpha and gamma u. So here instead of alpha, just alpha, we have two different parameters. So based on that, these different methods are named. And again, there are certain methods which are conditionally stable, and there is a condition to determine their stability. Okay, so all right then. Yeah, so now we have explicit and implicit time schemes. So to solve these problems, we there's one way that we can go by, that is if we convert our mass matrix into diagonal terms, your diagonal terms, then getting a solution is, you can explicitly get a solution whatever the right hand side term are. This is very direct. So this scheme is known as explicit solution scheme. It is of course very fast, uh, and it so happens that in some way the delta t critical also becomes large for this case. Uh, or if we can just go for implicit scheme, for that case we don't need to convert into a diagonal matrix. So to convert into diagonal matrix, there are two techniques which are known as, first one is known as row lumping scheme, row sum lumping, where we sum the all the elements of the row into and add it to the and put it to the replace it with the diagonal terms, and rest put all the zero. And then there's proportional lumping, where we take the proportion of each diagonal term and distribute all the sum based on that proportion. So yeah, this was it here in this method, in this with this week's stuff. And if there's any doubt, then I can take it now regarding this. So I'll wait for some time. If someone has to put a doubt, then we'll start the problems. Okay, then if there are no doubts, we can move forward. Okay, so we go back again to the weak form. So can someone tell me what is the first thing we do before writing a weak form in the final week of this course? Then I think this should be very much clear by now. So how do we start the problem while writing the weak form? If anyone wants to answer, they are welcome to unmute themselves and answer. All right, it seems we're not getting any answer. So first thing we do is write the weighted residual statement. Whatever equation we have here, so I'll write it as x. Then we perform integration by parts. We leave the time derivative term just like that. And we have sorry, it's a partial derivative now. and we have a boundary term as well. That would be, okay, I'll just write in terms of elementary coordinates. Sure. So now we have, sorry, this whole thing is equated to 0. So I'll not violate that. Yeah, sorry, more terms here. Then we have, plus I'll just leave this boundary term as this here. Okay, so this is what the weak form of this problem looks like. That's pretty simple, straightforward thing. I don't think there should be any doubt here. If there's no doubt, then we'll move forward. Okay, so now we need to use the backward difference method for temporal approximation of the previous problem. So before using the backward difference method, I think we need to discretize it in space first. So we'll do that here as well. So what is the assumption we take here? U is summation j equal to n. That is uj, which is a function of time, times vj, some function of space. And then of course w we can replace as vi. So what do we get here? It's pure space function, then we can write dvi dx dvj by dx vi vj times duj by dt, since uj is a function of time, and this is equal to 0 to h vi times our function f dx. So we can write this term as k. This would be a matrix, and then we can just write this term as m. This again would be a matrix, and this is actually a vector, which is u dot, and this term is again a vector, or f, right inside vector. Plus if we have boundary term, that would be included here. So I'm sorry, I missed uj term here, sorry. So this would give us, so now we need to perform our approximation, the alpha family approximation. Start with our, so what we have here is we have k, u, m, u dot f. So out of these, k, I think it's not dependent on time. We can this not care about it. U would change with time, so we need to worry about this. M won't be dependent on time, and of course u dot would be dependent on time, and f is also dependent on time. So f is a function of x and t here. So we'll have to take care of f as well. So our alpha family of approximation says that I think it's 1 minus alpha times u dot s plus alpha times u dot s plus 1, that is equals to u s plus 1 minus u s upon delta t s plus 1. So yes, this is what the equation looks like. So there's a long way to do this. I propose a shorter way to deal with these problems. So we identify the terms that are dependent on time, and we do something like this. Oh, sorry, it's gone. I accidentally locked my screen. Wait, let me reshare it. Sorry for the inconvenience. I'll just join back. Yeah, so we're here. So there's one thing we can do. We can write k as it is. So whatever term we have that is dependent on time, we can approximate that as, sorry. So here mass matrix is also independent. So for derivative time derivative term, we can replace it as this. And again, f we'll have to approximate like this. Okay. So now the next thing okay. So there's one thing we need to use backward difference method. So for a backward difference method, what is the value of alpha? Would someone like to tell this? please, if anyone wants to help me. I'll wait if someone is willing to help. Okay, then we'll go forward. So for backward difference method, the value of alpha is 1. So we'll just substitute it here and get things simpler for us. We have k times us plus 1. Then we have m times, we don't have any alpha term here. So what I'll do is, okay, we'll just do like this. S plus 1 minus u times, you get s times step delta t s plus 1, this subscript. Is there a doubt somewhere? Okay. Alright, so then again we will be left with f at s plus 1 step. Okay. So what we can do is we can separate the us plus 1 terms. K, sorry, it would be delta t times k. I'll multiply the whole equation by delta t s plus 1. We'll be left with delta t s plus 1 times k, and we can take m common here. That would give us, yeah, so coefficient of us plus 1 would be this. And then we have a us term that we'll take to the right hand side. We have our f vector calculated the new time step, and we have our, okay, sorry, this would also be multiplied by delta t s plus 1. Delta t s plus 1 times f of s plus 1, and then we have our mass matrix term. Exam pattern going to be, I'll answer that. Let me finish this. Okay, so this is our final equation that would give us a set of algebraic equation. So we have this combined matrix, and this would be a vector term. So m multiplied by u at whole time step will give a vector. You can add it to the new the vector f calculated the new time step, then we'll get a vector at right hand side, and with this matrix we can solve this equation to get our unknown at the new time step. Okay, so I hope this is clear. If there's any doubt, please let me know. And yeah, meanwhile, I got a question here. Yeah, how is the exam pattern going to be? So I think the course instructor might have told you that it would be an MCQ based exam. So you'll have MCQs only, and but there would be calculations required. So I think that's all I know from on my part. I don't think I can give you any more information for that. Is there anything else you want to know? Please let me know. Otherwise, shall we move on to the next topic? Okay, so we need to write the alpha approximation statement for alpha equals to 1 by 3. How many questions? I honestly don't have any idea. We are not given these kind of informations. And personally, I haven't given any NPTEL exam, so I can't tell you that. If you know anyone who has given these exams before, they might know it well. So we can mainly answer your doubts and queries regarding the course content. Yeah, yeah. Well, so yeah, so we have to write the alpha approximation statement for alpha equals to 1 by 3. So what was the alpha approximation statement? I think that's we just wrote it 1 minus alpha time dot s plus alpha times dot. I hope I'm writing the statement correct. I don't remember very well. If I'm doing anything wrong, please stop me and correct me. Yeah, and this whole thing is equal to us plus 1 minus us. One times, yeah. So alpha equals to 1 by 3. What will we have? 2 by 3 of the derivative at last step plus 1 by 3 derivative of new time step. And we have same question. Same question as in the last question. How many questions are you going to get in exam? Okay. So that's what we get here. This is the approximate statement. So we'll take we'll, to understand it more efficiently. We'll try to visualize it. So we have the value of u changing with respect to time. This is actually time axis, and this is the solution value u. So 1 mark or 2 mark? I honestly don't have any idea. So we'll take s equals to 1. This is t1. This is t2. So delta t2. We have u1. So what this essentially means is you can write this thing as 2/3 of u dot 1, 1/3 of u dot 2 is to u2 minus u1 upon delta t2. Okay, so the slope here between u1 and u2 can be approximated as 2/3 of this slope at this point, this slope, and 1/3 of, sorry, average of these two. Ah, yeah, so that's an average 2/3 plus 1/3. We take 2/3 part of this and 1/3 part of this, and we'll get an value between these. So that's a kind of an approximation. Again, we can't say that this is a stable approximation, but that's this. So yeah, we can move on to the next problem. Okay. So we know the eigenvalues for a FE problem. Lambda is given as 0, 0.2, 0.5, 0.7. So yeah, for alpha equals to 1 by 3, what is the critical time step? So yeah, alpha equals to 1 by 3. What is the formula of critical time step? Can someone tell me? Would anyone like to answer this? I'm not good with remembering formulas. Please help me. I really don't remember. If someone would tell, then I'll have to look up the notes and see. I think these type of little calculation problem would be asked in the exams. So we have some formula, the formula base given, which will be used to find these things. I'm not sure, but this speculating. Is anyone going to help me here? Fine, I'll have to think, try on my own. So I think I remember some part of it. 1 upon 1 minus 2 alpha times lambda, and that is the highest lambda value. So we'll be using this. Yeah, I'll just confirm this formula. Don't really remember it well. Oh, it's 2 upon 1 minus 2 alpha. Ah, my bad. 2 upon 1 minus 2 alpha. So 1 minus alpha is 1 by 3, so 1 minus 2 by 3 times 1.7. So we have 2 upon 1 minus 2 by 3 is 1 by 3. So 3 goes up, 2 to 3, 1.7. So 6 upon 1.7. So whatever the value of this thing is, we're not going to calculate this. So that's our time step, critical time step. So we can't go beyond this. Whatever the problem is, we'll have to keep a time step under this value. Okay, so there is no doubt we'll move forward. Okay, so we have to write the Newmark family approximation statement for all the unit derivative. Alpha equals to gamma equals to half. Given alpha half, given gamma half. So anyone wants to guess the statements? Let's start with you, right? I honestly don't remember this as well. Would Does anyone remember the statement? Would you like to test your memory? So for the new joinees, uh, we have to find the Newmark family approximate statement for these unit derivative terms for alpha equals to gamma equals to half. So we know the alpha and gamma values. Can we approximate these things? Please feel free to answer. So I just want someone to tell the formula for this. No one? I'll try it on my own. So U was US plus minus. Sorry, yeah, it's US plus 1 equals to US plus delta T times dot S plus delta T square by 2 double dot S plus alpha, I guess. Is it alpha? Yeah. No, it's gamma. Sorry. So, and this term is, sorry, this term, not this term. This term is given as, so gamma is half, right? So U double dot S plus half is equals to, I think that is same formula for alpha approximation. 1 minus, yeah. 1 minus half times U double dot S plus half times U double dot S plus 1, isn't it? Ah, sorry. So we can approximate US plus 1 as US plus delta T U dot S plus delta T square by 2 times half of U double dot S plus half of U double dot S plus 1. Okay, so for U dot S plus 1, we just take the derivative of the above statement. That gives U dot S plus delta T times U double dot S plus alpha, and this S plus alpha is again the same thing, S plus half, right? So that gives us half of U double dot S plus half of U double dot S plus 1. So we can get our U dot S plus 1 plus U dot S plus delta T times delta D by 2 times U dot S plus double dot s plus 1. And now how do we find our u double dot s plus 1? Anyone? Any idea? Any suggestions? I'll have to check the formula again. Yeah. So I told you that we substitute these values up back in the statement, we can get u double dot s plus 1. So I'll just use this statement here. M times. So I do it here. We have m times u double dot plus k times is s plus 1, k times u s plus 1 equals to f of plus 1. So u double dot s plus 1 is equals to m inverse times fs plus 1 minus k s plus 1. Okay. So that's how we can get a u double dot s plus 1. So that's how we approximate the primary variable and its derivative terms in case when we are in for Newmark family of approximation. Okay. So I hope there's no question here. Okay. And we go on to our last question. So we have a given solution at first time step u1. We know k matrix, we know mass matrix M, and we were given delta t 0.1. We know alpha equals 0. So that implies this is forward forward approximation. And we're given f equals to 0. So we need to find the solution at the next time step. So considering the given data in the problem, can we tell what type of equation we are dealing with? Please feel free to answer. What is the type of differential equation we are dealing with in this problem with the given data? Okay, so since we are given only one stiffness matrix and only one mass matrix, and there's only one approximation parameter alpha, So this is definitely a parabolic equation where we only have one time derivative term and only one second order term with respect to x. So I think we did some approximation for that in our first problem, first and second problem, right? So yeah. So here we did it for alpha equals to 1, but here we know we now have alpha equals to 0. So we'll just use this thing, and of course we are given f equals to 0, so we don't need to care about the right hand side term. We'll just use the left hand side thing with the coefficient of k and m. Just write it there. K times the alpha approximation of u plus m time. So we'll start with this. We have k times 1 minus alpha u s plus us plus 1 plus m times we have derivative term, so we write the u s plus 1 minus s on delta t, and then since we are given the first vector 0, we have the right side 0. Okay, so alpha equals 0 here, right? So we are left with k times us plus m times, so delta t is also here, m times plus m times us plus 0. So separating the terms, where we have us plus 1 terms on one side, and we have m minus delta t k times us. So now the time step we are dealing with is 1 and 2. I mean, we know 1, we want to find 2. So our unknown, this has to be 2, and this known has to be 1. So can we just write this as m times v2 equals m times delta t k times u1. Okay, so we'll try to do this calculation one by one. So first we find m minus delta t times k. So we have m as 210141012, and delta t times k is delta t 0.1, right? Just multiply every cell. So we can write this as 2 plus 2.0 minus here. We have 1.9. So 1 minus 1 minus a minus 1.1 0 0. We have simply 1.1 again. Yeah, 4 minus 0.2 is 3.8. Then we have 1 plus 1.1. Here also we have 1.1. Here will be 0. And this should be 0.9 again. So this is m minus delta t times k. And now we have to perform matrix and vector multiplication. So we perform minus delta t times k, this multiplied by u. So we have so what are u? The value u 0, 0.51. So we multiply this 1.1 times 0.5. Then second row we have 3.8 times 0.5 plus 1.1 into 1. Then in last row we have 0 times 0, 1.1 into 0.5. Then we have 1.9 times 1. So continue calculation below. That gives us 1.1 times half of 1.1 is 0.55, and 3.8 half of 3.8 is 1.9, and plus 1.1 we get 3, and half of 1.1 0.55 again plus 1.9, so 1.9 plus 2.45 I guess. Okay, so we have the right hand side, we calculate this term here. Now we are left with the equation. So m times u2. So m is, what is m? 210141 4101 2 times. So we'll write our u2 vector with, so we supposed to have 3 terms. So I'll write it as ua, up, uc is equal to the right hand side term 0.553 2.45. So we'll just distribute the equation and try to solve. So we have 2ua plus ub equals to 0.55. Then we have ua plus 4 times ub plus uc equals 3, Then we have UB plus 2 times UC equals to 2.45. Okay, so what we'll do is we'll substitute the value of UC and UA into second equation. So here from here we can write UA is 0.55 minus UB 0.2, and here also you can write same for UC 2.45 minus UB 0.2, and we can substitute these two values in this equation. What we'll get here is plus 4UB, and then for UC also we have 2.45 2 minus UB by 2 is equals to 3, and we can combine the UB terms. So minus UB by 2 minus UB by 2 makes minus UB plus 4 UB, that gives us 3 UB here, and on right hand side we'll take all the constant on right hand side. We have 3 minus 0.55 plus 2.45 by 2, and this gives us UB equals to 1, and then 0.45 plus 2.45 makes 3, and this 3 comes down at 3 by 2. We are left with 1 minus 1 by 2, that is again 1 by 2. UB is 1 by 2, and if we substitute the value of UB in first statement here, we'll get this as 0.55 minus 0.5 by 2, that gives us 0.05 by 2, that is 0.025, and same for UC, we can do this 2.45 minus 0.5 by 2, that gives us 1.95 by 2, so that is I think 0.975, right? So 925, I think. 1.95 is 1.95, then 0.125, 0.925. Okay, so what is our U2 finally? U2 vector, that is UA is 0.025 and UB is 0.5 and this is 0.925. Okay, so this is our solution. I hope this is clear. So that's all. That's for all for this session, and I, we are done with our syllabus for this course. If there's any doubt, then I can answer it now. Otherwise, we'll end our session here. Please let me know if there's any question here. Okay, if there's no question, then we'll end this session here. And with this, I would like to thank you all for joining me with this series of sessions. And if there's anything else you would like to ask any further doubts from me, you can contact me at my email address. And thank you all for your participation and your patience. And I welcome to I anticipate your participation in further sessions that I'll be conducting in later semesters. Okay. Yeah, I have a question here. Someone raised a hand here. Please, if there's any question, you can answer. You can unmute yourself and uh, ask. So there's no question. Can we end the session now? Okay, then if I'm not getting any response, then I assume that there's no further questions. Okay, thank you so much for participation. We'll end it here. Thank you.